What's up, everyone? Hope you guys are having a fantastic day so far. And today we're going to be going over a few examples on integration by parts so you can be prepared for your exams and you can learn a few new methods hopefully throughout this video. So without further ado, let's get right into it. So for our first example, we have the integral of 3t sine squared t dt. So right off the bat, we see that we have two functions, right? We have this 3t times by this sine square t. And right away, you should think of doing integration by parts. But that sine square t is going to be quite annoying because taking the antiderivative of that, it's not necessarily too hard, but it's not something too nice to do. It might be a little bit longer, a little bit complicated. So using our knowledge of trig identities, we can rewrite that sine squared t using the power reduction formula for sine squared, which is 1/2 times 1 minus cosine 2t. And if you've never seen that before, there's also a cosine one. The only thing that's different is the plus. There's a plus. It's 1 plus cosine 2t. These are very important. You'll need these throughout your Calculus 2 class. So with that being said, we can rewrite our integral as we can bring the 3 out because it's a coefficient. We have t times, and we're going to write this whole thing in that parentheses. So we have 1/2 parenthesis 1 minus cosine 2t parenthesis dt. And so since everything right here is multiplication, right there, multiplication right there, we can bring out this 1/2. We can completely bring out this 1/2 out to the front. So we'll have 3 times 1/2, giving us 3/2 integral of t times 1 minus cosine 2t dt. And now we have a much nicer looking integral, and this shouldn't be too bad. So let's go ahead and move down here. So what we're left with is we have the 3/2 on the outside. And let's go ahead and FOIL in that t, right? Make this easy. There we go. So now we just have t minus t times cosine 2t dt. A lot of t's. So now I'm going to go ahead and split this up into two integrals because we're going to have to do integration by parts right here, right? We have two functions being multiplied to one another. And we know that the integral of just t, right, is going to be 1/2 t squared. So we can kind of forget about that and bring that in at the end. So let's go ahead and work on this integral right here. We have this t cosine 2t dt. And so here we have another integration by parts, but it's much more simple, right? It looks a lot more simple than the first initial integral that we have. So what we can do, you can either choose to do the uv minus integral of v du method, which works perfectly fine. But a method that I'd like to show and that I'd like to use a lot and show a lot of students is the tabular method or the DI method, whatever you like to call it. So that's where we make a table like this. And the D stands for derivative and I means integrate. So when we have two functions, right, usually we do this when we have a function that's made up of two functions, right, integration by parts, where one of them is, when you take the derivative, it ends up going to 0. Right? T, taking the derivative of t, should go to 0 pretty quickly. And the cosine just repeats. Or it could either be an e to the x or any other trig function. Those are the perfect ones to use for this DI method. So on the left side, we're going to go ahead and use t, since taking the derivative of t a few times goes to 0, right? Derivative of t is 1, derivative of 1 is 0. And then we have to integrate just as many times as it took to get to 0 for the derivatives. So we have cosine t initially. Integral of cosine t is going to be 1/2 sine 2t. If you don't know where that came from, all I did was a quick u sub for the 2t, right? du equals t dt. Oops, sorry. 2 dt, and then the 1/2 du equals dt. That's the u sub that I did to get this, but it's not too bad. You can try it on your own. I invite you to try it. And then one more time, since we took the derivative 3 times, we have to take the integral 3 times. So now we should get, it's going to be this, it follows the same pattern. Since we have a 2t in the inside, that coefficient in the front is just going to be multiplied by 1/2. So then integral of sine is going to be negative cosine. So we have a negative 1/4 cosine 2t. And boom, that's all we have to do. If we take the derivative 3 times, we have to integrate 3 times. But the last step for this DI method is to multiply the top by -1. You always start with plus, and then multiply the next one by negative. And then we could do this by plus, but there's no need to do that. And then we need to multiply across, just like this. This first one doesn't get dealt with. Just start with the first D and go down and across, all the way until we get to 0. We don't have to do it again, right? Because if we were to integrate this again, we would just get 0 times that. So once you get to 0, you just stop. So what the antiderivative for this integral, all we need to do is multiply across. So we have that t times 1/2 sine 2t, and then -1 times -1/4 is going to be positive 1/4 cosine 2t. And that's it for that side integral. So for our total answer, bringing everything down, we still have that 3/2 on the outside, and I'm going to do a big bracket because we have a lot of stuff to multiply. We have that 1/2 t squared from that beginning integral, right? Pretty simple. And then we have a minus because of that minus right here that we had initially. A minus, and then parentheses to make sure we distribute properly. Then we have that t over 2 sine 2t plus that 1/4 cosine 2t, parenthesis, and then close it off with that bracket, plus c. And that's a totally valid final answer. You can go ahead and take your time if you really like to simplify it. Distribute this negative in, that's what I would do first. And then distribute this 3/2 into everything. But this is totally valid. I want to spend time doing the integrals, not algebra. So yeah, this is your final answer. Not too bad. Let's get on to 2 more. So on to the next example, we have this 9 times theta cubed times cosine theta squared. And this looks a bit complicated, right? We know we need to do integration by parts, but you can go ahead and approach this however you'd like. You can try it on your own. But a technique that I would like to do first is do a little substitution, a small use up to make this look a lot nicer and make this integration by parts a lot cleaner. Since what told me to do that is because this theta cubed right here can be split up into theta squared times theta, right? And look, if we were to do a u sub for the theta squared, this would also turn to u. So everything would look a lot nicer. So let's go ahead and try that out. Let's do u equals theta squared, derivative of both sides gives us 2 theta d theta. Now, getting that d theta by itself, we have du over 2 theta equals d theta. So now plugging everything back in, we can pull that 9 out in the front, right? Coefficients. Then that theta cubed, right? Like I showed, is made up of a theta squared and a theta. So that theta squared is a u. So we're gonna have u times theta, and we have this cosine still, cosine of u, right? Pretty easy. And then we have that du over 2 theta. And look, theta cancels out now nicely. We can bring this 2 right here is really a 1/2, right? It's being divided by 2, so it's really a 1/2. We can bring that out and multiply it by that 9. So we should get a 9/2 on the outside. And our integral is just u times cosine, of u, du. And now this is very easy, and we can go ahead and do that DI method again like I had showed previously. We just choose one side to take the derivative of and the other one to integrate. And we always want to choose, for the derivative, we always want to choose the function that will end up going to 0 or something that's nicer, right? So we have u, derivative of u is 1, 0. Then we need to do cosine u, integrate that. We have sine u, integrate that, we have negative cosine u. Remember, plus, minus, multiply across. It's the same process every single time. So bringing this all down, we have this 9 halves, and then our integral is going to be u times sine u, right? We multiply it across, and we have that -1 times negative cosine. Negative and negative, they cancel out, right? So we just have plus cosine u. We have a plus. Now, for our last step, we don't want our answer in terms of u. We want it in terms of the variable that we started off with, which was theta. So going back up here, we see that our u was theta squared. So all we need to do is plug in theta squared wherever we see a u. So now we're going to have theta squared sine of theta squared plus cosine of theta squared, right, plus c. And that's it. That's the final answer. Not too bad. I hope you guys are learning some new techniques here. This substitution that I did at the very beginning was not super necessary. You could still proceed with integration by parts, but whenever you can do a substitution to make stuff easier, it's always the best option. It always save you hassle. You might not you risk messing up if your integration by parts is very complicated. So and this is something that just takes time to recognize to use this U-sub. So don't be discouraged if you didn't know to do that. That's why I'm showing you guys these videos and these techniques, so you can maybe apply these to your own homework in your own exams. So on to the last example here for integration by parts. Let's go ahead and attempt this using what we know, right? When we do integration by parts, you know, the past few examples we've been doing the DI method, but here we don't really have something that's going to go to 0 nicely. We don't really have something that you can take the integral of nicely either, right? If we were to choose this for our for our D, right? How would we integrate that? How would we integrate the square root of x cubed plus 1? So I recommend, if you really want to try this out on your own, I'd recommend it, and you would see that it's just not a very standard integration by parts. So there's a few techniques that we can do here to make our life easier. We have to do a little bit of manipulation. Remember that we can maybe split this x to the 5th up, right? We can put the up into something like x cubed times x squared. And so if we rewrite our integral with that little bit of a manipulation that we did, it might make our life a bit easier, because now this is not super easy to recognize, but if we were to do this for our u, for our integration by part method, you know, the u v minus integral v du, if we made that our u and we made this our dv, we can integrate this. This is just a simple u sub, right? We have enough x's to cancel out if we were to do a u sub for that x cubed plus 1. So let's go ahead and try this out. So moving down here, if we make our u the x cubed, take the derivative of both sides, we get 3x squared dx. Now for the other side, we have dv, right? We have x squared times the square root of x cubed plus 1 dx, right? So if we do a quick little u sub right here, we can do u, or I'll do a different variable, t equals x cubed plus 1. dt is going to be 3x squared dx, right? And look, we have an x squared here. If we solve for dx, we get dt over 3x squared equals dx. This, we can rewrite this over here as x squared and the square root of t, right? That's the substitution we made. And then we have dt over 3x squared. And look, these x squareds cancel out, leaving us with 1/3 square root of t dt. Now taking the integral of both sides, we have v equals, and then remember, square root of t is just t to the 1/2. So reverse power, will add 1 and divide by 1/2 plus 1 of the new power, which should give us 2/3 t to the 3 over 2. So we have this 1/3 times 2/3 times t to the 3/2. And then multiplying that 1/3 in, we get 2 over 9. And then we have that t, the substitution we did, which was x cubed plus 1. And then it's to the 3/2 power. And there we go, right? So this was a little bit of a longer process, but now we have everything we need. We have our u, we have our du, dv, and our v. So now with the integration by parts formula, right? So let's go ahead and rewrite our integral over here. We have that x to the 5th of square root of x cubed plus 1 dx equal to uv. So our u is x cubed, and then our v is this big 2/9 x cubed plus 1 to the 3/2 power. Let's go ahead and move this down really quickly, right? And then we have minus the integral of v du. So our v is this 2/9 x cubed plus 1 to the 3/2 times our du, which is that 3x squared dx. So all this out here is done and dealt with. So this is part of our answer now. We need to deal with this last integral right here. And yes, it's getting pretty long, but this is a really good example to study on. So look, we have some coefficients, right? This 2/9 and this 3. Go ahead and bring that out completely. 2/9 times 3 is going to be 2 over 3, right? Then we have this x cubed plus 1 to the 3/2 power times x squared dx. So now we can go ahead and do another quick u substitution here. We can do u equals x cubed plus 1. Derivative of both sides gives us 3x squared dx. Solving for dx, we get du over 3x squared equals dx, right? So moving on over here, we have this 2/3 integral with our u to the 3/2 power times x squared times du over 3x squared. X squareds cancel nicely, so we're left with, we can bring this 1/3 out as well. So we have 2 over 9 times the integral of u to the 3/2 du. Now it's easy to integrate. Add 1 to the power, divide by that new power. So we should be left with 2/9 times, which should be 2 over 5, u to the 5/2. Plugging back in our u, we should have 4 over 45. And our u that we made was x cubed plus 1 to the 5/2 power. So now we're left with, this is what we have after doing integration by parts. So we need to go ahead and bring this down, like the beginning part right here that we had from our integration by parts formula. So we have, let's go see what we have. So we have x cubed times 2/9. And sorry, let's just zoom out so we can see. So it's x 2/9 of x cubed plus 1 to the 3/2 power. And we have minus, sorry, let's go and close this parenthesis right there. We have minus everything that we just got from here. So we have this minus, and then after what we got from doing integration by parts, we got this whole part right here. So we have minus 4/45 times x cubed plus 1 to the 5/2 power plus c. And that's it. Yes, that was a long one, but this is something that you should expect to see on your tests, on your homework. Nothing too bad. What we did, just to recap at the beginning, was We weren't able to do integration by parts easily at the beginning because we were left with an integral that we don't know how to solve. We don't know how to solve square root of x cubed plus 1, right? Just integrating this is really difficult. So we were able to split apart this x to the fifth and make it into something that can just be done with a simple u sub. So all this right here was just doing our u dv step for integration by parts. And then down here, we just have to do another quick little u sub. And it was not too bad. Just taking your time, making sure your work is clear so you don't mess up with your signs and your multiplication. And that's really all the advice I have. So thank you guys for watching. I really appreciate it. Make sure you like and subscribe and go follow my TikTok. I'll be posting a lot of videos on there. And thank you guys so much.